And hello, welcome everyone. Today we're going to continue where we left off in our thermal boundary layer equations. So this was the energy equation that we found ourselves reducing. We reduced the thermal energy equations to this. The energy equations to this, and mostly it's contributed to by thermal energy. So now we want to start cancelling off terms. Okay, first we assume. Okay, for the sake of speed, since done this before in previous videos, I'm just going to ignore the Z momentum or Z energy. Yeah, Z energy derivatives. So we assume 2D. So Z derivatives are zero. Okay, so of course in general we have 3D, but we can actually reduce it to 2D. Okay, of course. Yeah, so let's do that. We can cancel off the Z terms. We assume no variation with Z, so it's a 2D problem. Okay, so that takes care of these two terms. Okay, and there you go. Okay, so thermal, and let me put a qualifier there. Laminar boundary layer. There's a laminar boundary layer. If you want to talk about turbulent boundary layer, you can also refer to my turbulence modeling playlist. I have a whole playlist of that, so it's inside the video description, so you can take a look there. But this one's a laminar one. Okay, this is a laminar one. Okay, so now we have this. We can start non-dimensionalizing as usual. So one of these terms will actually drop off. Okay, so one of these terms will actually drop off. So let's use GIMP again, and let's start. Okay, well, again, just to give you a good visualization, we have a thermal boundary layer as so. Okay, so this is fluid coming in at U infinity and T infinity. All right. And this flat plate will have a velocity at the surface us, which is usually assumed as 0, but it also has a ts, which is whatever you want it to be. Okay, so velocity of the surface equals to 0 usually. So the importance is the relative velocity between this U infinity and this S. That's the important velocity. If US is some finite value, US equals to 5. Okay, to make the problem easier, we kind of do some shifting of the reference frame, so to speak, so that we take it from the reference frame of the boundary plate, so that the US is 0. Velocity of the surface is 0. Otherwise, it's a more hassle to solve. But TS cannot be assumed 0. Okay, we cannot do the same trick, so we have to assume we have to assume that TS is not absolute 0, otherwise you can't have fluid flow boundary in a boundary layer like that. And of course T infinity cannot be absolute 0 as well. So okay, not so good. Or you cannot just assume it's 0 degrees Celsius. There is an absolute temperature scale that you have to abide by. Okay, so how then do you do all of this? Okay, so since we have to take care of this relative problem, we need to introduce relative temperature. Okay, so the relative temperature is equals to okay, we always use relative temperature, which is T minus T at the surface. Okay, so what's important is not for this boundary layer, it's not the absolute temperature. Over here, it's not the absolute temperature, it's the temperature difference between here and here. Just like for velocity, the importance is the temperature. It's the velocity difference between this free stream velocity and the plate velocity, which in most cases is just 0. Okay, so we always use relative temperature and relative velocity just that in a thermal boundary layer it's a bit more in the face, so to speak. Okay, more obvious. So we like to use this variable T minus Ts. Okay. Okay, but the good thing for us, okay, partial by partial x. Okay, a derivative of anything, T minus Ts, for example, equals derivative of is a derivative of T. So long as Ts is constant, so long as Ts is constant, you can just introduce this in like that. Okay, when Ts is not always constant, it's not as easy to do a trick like this. Okay, so yeah. So for the simplest of cases, we assume a constant temperature plate. Okay, there are other cases where the plate may not be at a constant temperature. You may prescribe a heat flux to it, but that's a different case altogether. I'm not going to go through that first. There's a bit more work to do. Okay, so 6 minutes in. Yeah. So let's start non-dimensionalizing. So okay, not non-dimensionalizing yet. That part will have to wait. So let's replace everything up by relative temperature, because these derivatives are the same. All of these are temperature derivatives. They're not actually like actual temperatures. Okay. Okay, so let me get rid of this. And now quick build. Wow, looks like the LaTeX Maker UI changed a bit. I just noticed that. Okay. Anyway, so after this is done, we want to start non-dimensionalizing again. So the most obvious way to non-dimensionalize is wait, before we non-dimension, yeah, should we non-dimensionalize first? Yeah, I think we should. So we want some order of magnitude analysis so that we know what terms we can cancel out. Of course, some interesting numbers will pop up again. Okay. So let's see which terms we can neglect. So that will be done using the same dimensionless analysis, excuse me. Okay, so we can define the dimensionless temperature as follows. Ts will be the following. For temperature, it is the following. Okay, T minus Ts. Okay, so this is the relative temperature at any point versus the relative temperature at T infinity. I mean at the free stream. And if you want to take a little bit more a good how to say, if you want to take a if you want to look at some examples on the online, some useful resources, you can actually Google. I think this one's really good. I don't know how to pronounce his name, but it's from Sahan University of Technology. You can look at some of the notes over here. I'll just post a link to this in the description. It's not my work, but I think it's a good reference. Okay, in case you want to take a look at some alternative lecture notes, or yeah, you can see for yourself that yeah, I'm not making too many mistakes or something like that. Okay, so let's have theta being the relative temperature at wherever you are in the boundary layer or outside even, versus the relative temperature at the free stream. So it is very similar to U star equals to u divided by u infinity. So for temperature, we like to use theta. So this u is the relative velocity at anywhere in your free stream. It's actually u minus 0. Then they have the free stream relative velocity in the free stream, which is u infinity minus 0. They are both relative to the flat plate. So in case you're confused by the extra minus signs here, don't worry about it. They physically mean the same, very similar things. Okay, so let's non-dimensionalize temperature. Okay, let's non-dimensionalize temperature. So what do? We just replace T minus Ts equal, that will be equal to theta times T infinity minus Ts. Okay, so we'll just do T infinity minus Ts and put theta in front. T infinity minus Ts, for the most part, we can assume it is a constant. If you have a constant temperature plate, we can assume this is constant, though again, it's not always a constant temperature plate, and that's a different story altogether. Yeah, so this is how we do it. And conveniently for us, T infinity minus Ts can just be taken out and divided through, because all of it is a constant. So we divide throughout, and then we'll just get the whole thing in theta, which it's helpful, but the equation form looks more or less the same. Right, the equation form looks more or less the same as what we had before, and theta is on the order of magnitude of 1. So that's the useful thing. We need to make sure that all of these non-dimensional terms are on the order of magnitude of 1. Okay, so if you notice this equation form, alright, why not before I do that? Okay, we'll continue non-dimensionalizing to see which terms we can neglect. So let's see. Let's now non-dimensionalize the length. So what's the x length? X length will be, or rather x star, as if you can recall, is equals to x divided by L. Some people like to use star, some people like to use prime, really whatever floats your boat, man. Okay, and what will be the y star? Y star equals to fraction y divided by delta. And this time, I want to make it very clear that this delta is actually delta T, which is the thermal boundary layer. Okay, so thermal boundary layer is a bit different from the momentum boundary layer. In general, thermal boundary layer is different from momentum boundary layer. In general. Okay. So we can do that, but we can also say this thermal boundary layer is much bigger than, much smaller than L, so that makes it easy for us. So let's substitute in, and the time we can actually do it later. So x equals to x star times L. So let me bring the L out. 1 over L. Okay, 1 over delta T. So this will be y star. Okay, partial x squared 1 over L squared one over delta T squared. Okay. Let me put back the stars. Excuse me. So y star squared, and then I'll have x star squared as well. Alright, and there we go. Okay, so now we take a look. We have u over L, and of course we can actually change this into a u infinity term. Let's put this back. U star equals to u over u infinity. Okay, u over u infinity. And we can put it back. So u star u infinity. Okay. Okay, V will be based on our, because we assume no convection, right? Okay, no natural convection. We assume no natural convection. Okay, so V is actually, we assume no natural convection, so the relationship between U and V will be the same. It will be sort of the same idea, continuity equation. Okay. Partial x plus partial V partial y equals to 0. Okay, but now I have to notice this. Sometimes y over here in the momentum, if we were to use momentum non-dimensionalization, okay, if we were to do it the traditional way in our Blasius boundary layer, okay, we notice that y star is not actually non-dimensionalized using the thermal boundary layer thickness. Instead, it is non-dimensionalized using the momentum layer boundary thickness. Okay. Okay, so if we were to use momentum non-dimensionalization, we would usually take this as y star, and we can then sort of get an order of magnitude estimate for V. Okay, so this is how it is done, and I know it kind of adds a little bit more complexity now, but we'll have to go through with it. Fraction partial u star, so u equals to u star multiplied into u infinity partial x star. Okay, so fraction u over L. Yeah, so that's the first one. Then we'll do the second one. We'll do the second bit. Okay, Okay, V star will be, again, you have some characteristic V velocity, and then Y star will be using a momentum layer boundary thickness. Okay, and if you notice these two terms are on the order of magnitude of 1. Oops. Again, we'll just divide throughout. Okay, so VC. Okay, we'll just divide throughout. VC will be at the bottom. The characteristic V velocity, and then the P will be on top. And since both of these derivatives are on the order of magnitude of 1, they have to be, because we set the non-dimensionalization like that. Again, I think you may have done this before. U delta P VCL equals to math cal O of 1. Okay. So the characteristic V velocity will be on this order of magnitude. Okay, L. I think I forgot the U infinity there. Let's change that up. So I have to take L away. Okay, I think no, I want to do it like that. VC. I just put L over here, and that's how you get our characteristic V velocity. And VC is basically order of magnitude of 1 times this thing. So we can just set VC to be this, equals to this thing over here, so that V star equals to V over VC equals to math cal O of 1. That's how we usually do it. So it's a bit of a repetition of what I did last time, but just for revision. If you forget how to get VC, we always go back to the continuity equation. So yeah, I mean, if you leave the order of magnitude of 1 here, it wouldn't really make a difference, because you just set order of magnitude of 1 in the denominator. It will be the same. Yeah, so if you just set this, you substitute this whole thing in the denominator for VC, it's still order of magnitude of 1, so it still works. So regardless, we can actually just set VC equals to infinity delta P over L. Because whether or not we put in the order of magnitude of 1 term, it is still going to give us the same order of magnitude, which is what we want. We want to reduce all non-dimensional terms to order of magnitude 1. So we substitute this back in. Okay, so let's put this in, this VC in, and we'll just substitute that V star, this out for V star. Alright. Okay. Now we can put this delta T together at the bottom here, because now this boundary layer thickness is a little bit different. Okay, so we have two boundary layer thickness we have to mess around with now. It makes it a little bit harder. But when it comes to order of magnitude analysis, we can still say that all of these non-dimensional terms are on the order of magnitude of 1. That's fine. Okay, that's the main idea we want to keep here. Now is to find a non-dimensionalization for time. Okay, so T equals to fraction. Okay, T equals to T star over T characteristic. T star over T characteristic. What is characteristic time? Characteristic time will be U infinity, or L over U infinity, right? L over U infinity. Okay, because this is the time scale. T over L over U infinity. Okay, this is if you want to talk about hydrodynamic timescale. Okay, if you talk about hydrodynamic timescales, this is what you would use, and this is what we probably would use in our original boundary layer derivation. But the thing is, this thing here is not actually talking about hydrodynamic timescales anymore. We have to use thermal boundary layer timescales. So what are the timescales that have to deal with how do you say? What are the timescales that deal with thermal boundary layers? Okay, one clue is that there's this alpha here, which is actually thermal diffusivity. Okay, so what I'm saying is that the rate at which this thermal boundary layer starts to form is based on alpha. Okay, it's based on alpha. It's based on alpha among other things. I mean, there's a relative speeds, right? There are relative characteristic timescales between the velocity hydrodynamic timescale and of course the thermal timescales. Okay, those are for transient problems. Okay, but if you don't want to think about this headache, okay, for simplicity, we may not want to consider transient timescales in flat plate boundary layer analysis. So we make life easier for ourselves. We skip this part. Okay, we assume delta theta delta t is 0. We assume steady state. So we don't have to deal with this headache. Okay, so let's not deal with this headache for now. And then we'll just have our steady state sort of version. Now the thing is, we can probably combine everything together. We can probably combine everything together so that we can get a rough idea of what to look for. Okay, so let's bring some of these terms over to the right hand side. Okay, especially at least the U infinity over L. Let's bring it to the right hand side. So alpha will be on top, and then I'll have L over U infinity at the bottom. Let's get rid of the stuff here. Okay, Now you see this thing, delta P over delta T. Okay, delta P over delta T. We don't know what the ratio of it is in general. So in general, we want to keep this term. We don't want to just make it disappear. It doesn't work. Okay, so we just leave this term here. We play safe. Okay, we have alpha over u infinity on the right hand side. Okay, which is a common factor across all of these terms. Okay, but let's see. Okay, but we can make this observation. Okay, we are not going to non-dimensionalize fully. We can make, we already non-dimensionalize fully, but we are not going to try and extract some special Reynolds numbers or whatever over here. We can, but for now, not yet. Okay, we can make this observation. Okay, all terms on the left hand side we want to keep, but you see the terms on the right hand side, L square is usually much bigger than delta T square. So even if it's a thermal boundary layer, okay, oh, I think I'm overshooting time by a lot. Oh great, 30 minutes, okay. So I'll just make this point, I'll stop. So L square is much bigger than thermal boundary layers, so this term here we can cancel. This term here we can cancel by virtue of this L square. Everything else we keep. Okay, because we don't know what's the relative order of magnitude. But this for sure we can cancel. So let's cancel that term. So we cancel this d theta dx square term. Alright, so the rest of it we leave it here. And this is our non-dimensional form, which we'll just leave it first. And let's see. Okay, Ts is constant. Oopsie, it should go down. So the 2D derivatives are here. Okay, so if we don't have this relative temperature thing, and we assume steady state, okay. Okay, we can, and performing boundary layer analysis. Okay, we can get rid of the time derivative term and this x square term by virtue of x being very big. Just by non-dimensionalization we can do that. So this is the energy equation for our boundary layer. And of course we assume a lot of other things at the start as well, so you need to take that into consideration. No dissipation, no heat generation. Also, no dissipation or heat generation. Okay. And that's it. That's it for this boundary layer analysis. Very you can do it pretty intuitively. So we'll just leave it as such here, and the next video we will talk about some ways to solve this equation. Okay, thank you for watching. I'll see you again.